So it's a great honor to introduce Professor Christopher A. Fuchs, an internationally recognized scholar in quantum information theory and the foundations of quantum mechanics. He currently serves as Professor of Physics at the University of Massachusetts, Boston, where his research explores deep conceptual questions at the intersection of quantum theory and probability. Professor Fuchs received his PhD in physics from the University of New Mexico in 1996, where he worked under the guidance of Carlton M. Caves on the topic distinguishability and accessible information in quantum theory. He holds dual bachelor's degree in physics and mathematics with high honors from the University of Texas at Austin, where he conducted research under the legendary physicist John Archibald Wheeler. Following his doctoral work, Professor Fuchs held several esteemed research appointments, including the Lee A. Dubridge Prize postdoctoral fellow at the California Institute of Technology and senior research positions at BBN Technologies, Bell Labs, and the Perimeter Institute for Theoretical Physics. He has authored or co-authored more than 170 scholarly publications with over 19,000 citations, reflecting the depth and influence of his contributions. A standout among them is his co-authored experimental work, Unconditional Quantum Teleportation, which was selected as a top 10 breakthrough of 1998 by Science. Professor Fuchs is best known for founding and advancing quantum Bayesianism or QBism, a distinctive interpretation of quantum mechanics that recasts quantum probabilities as subjective degrees of belief. Sorry for this. For his groundbreaking work, he received the International Quantum Communication Award in 2010 and was elected a Fellow of the American Physical Society in 2012. Most recently, he was named to the 2023 Vox Future Perfect 50, which highlights influential thinkers addressing global challenges. In today's lecture, Professor Fuchs will guide us through QBism's ongoing efforts to reformulate quantum theory from a Bayesian perspective, touching upon open mathematical problems and new frontiers in quantum information science.
All right. Thank you for that very flattering introduction. I hope that I'm not too technically challenged. I'm going to try to bring my slides up. I've been asked to give a talk on anything that I want, and well, what I always want to talk about is a kind of movement that we call Cubism. I am introducing it with a piece of art by Marcel Duchamp, an early Cubist in the art movement sense. It's titled, the real thing is titled Nude Descending a Staircase #2. I have a play on that, and I promise you that I will keep my clothes on for this lecture. Everybody, I guess, gathered here knows that it's the soon going to be the 100th year anniversary of quantum mechanics. This started, or the usual marker for starting quantum mechanics is Werner Heisenberg's trip to Helgoland Island in June of 1925. He had a very bad case of hay fever, and so he went to this island where there were no trees and very little pollen to try to clear it up. And during that time, he had the insight of using a new kind of multiplication rule for calculating things. And he wrote an early paper and gave it to his advisor, Max Born, and in early July. Max Born looked at the paper after he submitted it and realized that what Heisenberg was doing, his new multiplication rule, was just nothing other than matrix multiplication. And Born quickly came across the idea of the canonical commutation relation, and really thus was born quantum mechanics. That paper was submitted by Born and his student Jordan on September 27th, 1925. So maybe that should really mark the 100th year anniversary. But as everyone knows, quantum mechanics is sort of plagued with some troubles. Here's something that David Merman said when quantum mechanics was about 90 years old. Quantum mechanics is the most useful and powerful theory physicists have ever devised. Yet today, nearly 90 years after its formulation, disagreement about the meaning of the theory is stronger than ever. New interpretations appear every year. None ever disappear. So what is cubism? Well, it's just another damned interpretation to add to the list, but it's marked out in a special way in that David Merman himself, by 2014, considered himself a promoter and a believer of the point of view. So I want to tell you about this view, cubism, and really what its goals are. The main goal of it is to be a magic pistol for shooting down all of the various mysteries of quantum mechanics. But in the process of that is meant to be a basis for finding new physics, physics that hasn't been found before. It really took its starting point when I was a student with Carleton Caves, and we were studying the works of a great Bayesian Edwin Janes, E.T. Janes, and we came across a paper that said, our present quantum mechanical formalism is a peculiar mixture describing in part laws of nature, in part incomplete human information about nature, all scrambled up together by Heisenberg and Bohr into an omelet that nobody has seen how to unscramble. Yet the unscrambling is a prerequisite for any further advance in basic physical theory. We took that as our inspiration and worked hard at thinking, how might we unscramble the omelet? And the key idea that we got from Janes was that whenever a probability is mentioned in a theory, no matter what the theory, then it should be understood in the Bayesian way, that a probability is not something that's out in nature, but rather something in your head. So if quantum mechanics is talking about probabilities, then it should be that there should be a Bayesian way of understanding those probabilities. And if one can take the Bayesian way and carve it out sufficiently well, then perhaps one can start to see what the real physical content of the theory is. So by 2002, our little group, we were all much younger then, especially me, we wrote our first paper titled Quantum Probabilities as Bayesian Probabilities. That got the ball rolling, but the thing that we didn't appreciate at the time that we wrote the paper was how many flaws and inconsistencies were in it. And we started to realize this slowly, and these were like little holes in the hull of a ship, letting water leak into the ship, and the ship was sinking. In an effort to make the point of view fully consistent, eventually we had to adopt a much more radical form of Bayesianism than Janes himself had adopted. We ended up, one can almost think of the Bayesian movement as a continuous spectrum from a very conservative end to a very liberal end. And where we had to go in order to fix all of the holes in the ship was to take the very liberal point of view promoted by Bruno De Finetti, who famously wrote in the introduction to one of his books this little thing where he says, my thesis paradoxically and a little provocatively, but nonetheless genuinely, is simply this: probability does not exist. He wrote in the center of the page in all capital letters. What he meant by that was, well, of course they exist, people use them, but you shouldn't think of them as factual features of nature. So, whether it's raining or not is a factual feature of nature. The weather report or the weather forecast that it's 75% chance of rain is not a factual feature of nature, according to Definetti and according to Cubism. Well, it turns out that taking that point of view has profound implications. The key one is this. In quantum mechanics, we always start with a quantum state and then use that entity, that mathematical entity, to calculate a probability from it. But one of the things that we have learned from quantum information theory is that if we consider the probabilities for the outcomes of a sufficiently robust set of measurements, then those probabilities will uniquely determine a quantum state. So it's not only the case that we can calculate probabilities from quantum states, but the mathematics of quantum mechanics, of quantum information, tell us that we can go back the opposite way. So the profound implication was this. We were left with the ghost of Definetti. My thesis, paradoxically and a little provocatively, but nonetheless genuinely, is simply this: quantum states do not exist. In other words, just like probabilities, quantum states cannot be factual features of nature. That's really the defining feature of Cubism. But I have to tell you, philosophers hate it, absolutely hate it. And it always boils down to essentially this. They start crying, wah, 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 your wave functions aren't real. But they have to be real because my philosophy says so. Well, why would we bring on the anger of so many philosophers? Well, the reason was that if we took this point of view, it had immediate explanatory power. We could explain the no-cloning theorem, quantum teleportation, Schrodinger's notion of steering, all of these various things that look great and mysterious actually all arise from the essential idea that a quantum state is not a state of nature, but a state of mind. So it had immediate explanatory power, but it also pushed new physics upon us. We ended up with a theorem that we called the quantum Definetti theorem. Now, if you look it up on Google Scholar, you'll find hundreds of citations to it. It motivated something called the no broadcasting theorem. The no broadcasting theorem, similarly, is a primitive thing for understanding quantum cryptography, and it's probably near 1,000 citations by now. So it had immediate explanatory power, but it also, in making the point of view consistent, led to new physics, things that wouldn't have been discovered otherwise. Niels Bohr had a nice way of putting it. He said, I felt that philosophers were very odd people who really were lost because they have not the instinct that it is important to learn something and that we must be prepared really to learn something of very great importance. That's the way he viewed quantum mechanics, that with quantum mechanics, we've learned something of very great importance about nature. But it didn't stop there. When one pushes Cubism to the limits, I think we've learned even more than Professor Bohr learned. For instance, Bohr would always depict measurements as these very heavy mechanical devices that were bolted to the lab table. But if one takes Cubism seriously, one finds that one has to give a treatment of measuring devices that is just essentially the same things as quantum states, and just as quantum states are equivalent to probability distributions, and probability distributions are not factual features of nature, measuring devices, the quantum description can be turned into an expression of conditional probabilities, and conditional probabilities, like any probabilities, are not factual features of nature. So among the things that Cubism has eventually led us to understanding. One of them is that the notion of quantum measurement really doesn't fit along the lines of the way Bohr described it. A quantum measurement is any action whatsoever, like, for instance, me picking up this coffee cup. This is me taking an action on the world, and its outcome just is the consequent personal experience this induces in the agent. I take an action and it induces some experience for me, tasting coffee, for instance, and that's the consequence. Quantum measurement outcomes are not, to paraphrase Bohr, instances of irreversible amplification objectively recorded for everyone to see in a device whose design is communicable in common language, suitably refined by the terminology of classical physics. It's not that, it's something else. And really, we learned from that we should probably change the vocabulary for what counts as a measurement. From John Archibald Wheeler, that was mentioned in the introduction to me, we've taken the idea of the participatory universe. Wheeler depicted it this way. He says, quantum mechanics evidences that there is no such thing as a mere observer or register of reality. The observing equipment, the registering device, participates in the defining of reality. In this sense, the universe does not sit out there. So we end up with a picture of the quantum observer that's basically a superhero that takes part in what the world itself is doing. When Captain Cubism takes an action on a physical object, it leads to something new being created in the world. So that's the point of view of Cubism. It's subjective probabilities, and the subjective probabilities are about personal experience. But then you might ask, well, what is the formalism about then? Physicists really want to know about reality. So it should be that the formalism is somehow expressing an aspect of reality. But another thing that Cubism has learned is that it expresses it normatively, not as a fact, but as a should be. So let me try to give you a sense of that by quoting one of the founders of this very subjective Bayesian version, Dennis Lindley. Lindley wrote, De Finiti's paradigm, the topic studied is the situation of an individual who is faced with uncertainty about some events of concern to him. All of us find ourselves in this position. De Finiti's task was first to recognize openly the uncertainty surrounding us. We live in an uncertain world. We've got to recognize that we do, and then see how best we can understand it. The paradigm is egocentric. It is the tale of a single person contemplating the world and not wanting to be stupid. What Lindley was really meaning is that a full-blown development of this idea leads us to decision theory. What probability theory is about really is making better decisions, or as Leonard Savage put it, how to gamble if you must. So let me give you some kind of sense of what it would mean to try to not be stupid. Here's an expression that we find in probability theory. If E and F are mutually exclusive events, probability theory says that P of E or F equals P of E plus P of F. In this subjective Bayesian view of De Finiti, each one of these terms are subjective judgments. It might be that you come to your judgment about the event F from reading one newspaper, and E, you find that you get better opinions from talking to your neighbor. And for this, maybe it's from still a third source, perhaps a third newspaper. And you want to use all of these probabilities for making decisions or making gambles. The normative reading of probability theory is, even though these three entities, these three judgments come from different sources, they had better fit together according to this equation. If they don't, then you're being stupid. In other words, you should rethink the probability assignments that you've made and adjust them ultimately so that they do achieve this equality. Now, that often takes some effort of the will. It's not, again, they're not factual features of nature. So if your probability assignments that you first think up don't fit this equation, then you have to hammer them and beat them into shape until they do fit this equation. So that's what the normative reading is about. But also look what we learn from it. It tells us that not everything is subjective. The individual terms in our equation are subjective, but the equation that they must satisfy is third person. It's invariant, anyone who's using it. It's the norm that is agent independent. Well, cubism views the formal rules of quantum theory as an addition to the book of decision theory. Instead of just simply being how to gamble if you must, what cubism views quantum mechanics about is how to gamble if you must in a participatory universe. And you must. In other words, how to gamble if you take into account that you are like Captain Cubism and that your actions are helping create aspects of the world. This leads us to a mathematical problem. So I told you that cubism is two things. It's about settling the quantum conundrums, or maybe three things, teaching us something about reality, but also as a motivation to invent some new physics. So we want to view the formal rules of quantum theory as an addition to the decision theory book. This gives us the motivation to go to all of the key rules in quantum theory and try to understand them in purely probabilistic terms. For instance, the Born rule for calculating probabilities. We have a probability on the left, but it equals a combination of these abstract operators, Hermitian operators, a quantum state and a measurement operator. Rho is a quantum state, E sub j is a measurement operator. When you look at this, it looks like the terms on the right-hand side are of a logically distinct character from the term on the left-hand side. The left-hand side is a probability, but on the right-hand side, there are these other entities that are not probabilities. They're matrices that involve complex numbers. What we'd like to do is find some different way of thinking about this rule, for instance, but similarly the Schrödinger equation and other equations within quantum mechanics. The key hint comes from Richard Feynman in a 1951 paper titled The Concept of Probability in Quantum Mechanics, where he very quickly says, despite the title of the paper, the concept of probability in quantum mechanics is the same concept that one uses for everything else. And he was a proto-Bayesian himself. He said, the new theory asserts that there are experiments for which the exact outcome is fundamentally unpredictable, and that in these cases one has to be satisfied with computing probabilities of various outcomes. But far more fundamental was the discovery that in nature, the laws of combining probabilities were not those of the classical probability theory of Laplace. So here's what he really pinpointed for us, that what is new and unique in quantum theory is the rule for combining probabilities. So what we take from that is that maybe this, the Born rule, is in a hidden way, a new kind of way of combining probabilities. Well, okay, Feynman had the double slit experiment in mind when he was saying that. And, he has famously said, we choose to examine a phenomenon which has in it the heart of quantum mechanics. In reality, it contains the only mystery. So then he goes on to show how one can talk about what happens when you have detectors at the slits versus what happens when you don't have detectors at the slits. You get two different probability distributions. And he says, but actually there is a connection between these two different probability distributions that one can ferret out or one can find by introducing complex amplitudes. So that's all good and it works mathematically, but Cubism says actually that way of thinking about it distracts from the seminal point that he had made already in 1951, that it's not about introducing new entities like complex amplitudes in quantum theory, with quantum theory, but rather to understand that it's the rules of combining probabilities that is changed. So this led the Cubists to attempt to modernize what Feynman had talked about. And this is going to be something that I won't go into as many details as I would like to, but because I don't have the time for that. But I'll just jokingly or tongue in cheek, I'll call it the D squared non-orthogonal slit experiment. Well, really, there are no slits, and so it's and it wouldn't, you wouldn't really know what to do about a non-orthogonal slit. And so let me tell you what it is. It's what is depicted here is a quantum system that is going to be thrown into a first measuring device. This is like going through the slits in the double slit experiment. A measurement will be made there. Potentially a measurement will be made there. If the switch is on, the measurement is made. If the switch is set to off, the measurement is not made. If the switch is on, then the quantum system goes in, a measurement's made, and it reemerges, the quantum system reemerges in some new quantum state that I'm calling sigma sub I here. And then it goes on further to go into another measuring device. So you can think of this as this is like the gun that sent out the electrons back in this picture. And then there was potentially measuring which slit we're going through. And then there's a final measurement at the end. But now I've generalized it. Particularly, I've generalized it in this way. In place of the slits, I'm going to use something that in quantum information theory is called a minimal informationally complete measurement, or a MEC, M-I-C, MEC reference measurement. And in place of the screen at the back, we're going to allow any quantum measurement whatsoever. So it's not just finding the position of the particle on the screen, but any kind of measurement whatsoever. For instance, measuring the momentum or measuring a combination of position and momentum, etc. Notice the way that I've got this depicted. So the quantum state here is depicted as an abstract operator. That's why there is a hat over it. The measurement outcomes of the intermediate measurement have little hats. These are operators. These are sets of operators, and that's why there's hats there. And the measurement outcomes of this other measuring device, again, is a collection of operators, and therefore hats. Under this, you see the P of Ri. What that represents is the probability of outcome Ri. And over here, we could talk about the probability of outcome Ej and the conditional probabilities of Ej versus Ri. Okay, so this is the full diagram. It's got all of the quantum mechanical entities. All of those have hats, and it's got the probabilities that they generate. Now, I want us to do something conceptual. Suppose we take this diagram, and if I could do it with my laser pointer here, suppose I could erase this operator and erase this set of operators and erase this operator. So I'm erasing them out of the picture, and that's depicted here. So now I've got a picture of a measuring device, another measuring device, and I've erased the quantum mechanical origin of all of the probabilities, but I'm still leaving the probabilities in the picture. So I've erased all the details of the quantum business. Can we still say how these various probabilities should be related. And the answer is yes. They're related according to something called the law of total probability that comes out of the book of decision theory that I showed earlier. You can give an argument for it called a Dutch book argument that essentially says, unless this relation holds between all of the probabilities depicted here, if this relation doesn't hold, then you're being stupid in some way and you can lose all of your money by bad gambles. I am going to introduce a kind of vector notation now, just so that my next equations can be simpler. Think of the numbers here, P of Ej, as elements in a vector. And think of the conditional probabilities as elements in a matrix. Then what this can be rewritten is vector equals matrix acting on another vector. So this, in essence, is the law of total probability written in vector and matrix notation. Now, I said we get this relation between the probabilities if the switch is on. But what if we turn off the switch? If we turn off the switch, this measuring device basically disappears out of the picture. And what happens is the quantum system goes straight through it, unaffected. And then there's the final measurement outcome at the end. Well, there are no probabilities in this story to connect anymore. There's only the probability of the final measurement outcome. Now we have to use the Born rule to give our guidance. It doesn't appear that we can erase these operators here because they are a crucial piece of the Born rule. We can't erase this operator here. So we don't have a relation between probabilities, or it doesn't look like we do. So you get this dun 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 moment. Actually, if you do a little mathematics, you can re-express the probabilities given by the Born rule in terms of the other probabilities that we had introduced earlier, according to a little equation that looks like this, where we have vector equals matrix times another matrix times a vector. And that new matrix we'll call the Born matrix, and it's defined most easily through the inverse. What it depends upon are these operators Ri and sigma j, which uniquely characterize what this intermediate measuring device is doing. So there we go. The Born rule that started out looking like this actually can be written in terms of probabilities only. This is a completely general statement of the Born rule. It works for any possible measurement. It makes no use of operators or state vectors, and it makes no use of complex numbers. So we now have an expression of quantum mechanics, one of the key equations in quantum mechanics. We have an expression that doesn't use any complex numbers at all. So let me just reemphasize this. The Born rule, born again. This is a formal expression of the Born rule that looks almost exactly like the law of total probability. The difference is, in the law of total probability, the extra matrix in here is simply the identity. But in the Born rule, it's something else. It's a matrix that's not equal to the identity. What we see is the expression on the left refers to probabilities in the switch off experiment, and the expression on the right consists of probabilities that refer to the switch on experiment. So these are two different experiments. It's not a contradiction to the law of total probability. So here's what we've learned from quantum mechanics, that the formal rules of quantum mechanics are about how to interrelate probabilities between different experiments. The old Born rule is still semi-visible in this formulation because this probability here is just the probability that we had before, but it turns out that these probabilities represent the measurement operators, and this probability distribution represents the quantum state uniquely. So this represents quantum state uniquely. This represents the measurement operators uniquely, but there's this extra matrix. But cubism says, look at this rule and now read it normatively. Recognize that all probabilities are subjective probabilities, and what the Born rule is about is it gives you guidance. It says, if you've come to this probability distribution from the description of your laser that the manufacturer made, and you come to this probability distribution based on the calibration that you've done in the laboratory, and this probability distribution because you've been reading a paper and you think that this is what it ought to be. Those numbers had better fit together according to this equation, or you're being stupid in the sense that Lindley said, stupid against nature. You could lose your shirt when you gamble based on these probabilities if they don't fit this equation. My advisor for the quantum teleportation experiment that we did in 1998, Jeff Kimball, he just recently passed away. He once told me that sometimes you have to put a gun to nature and say to nature, you will do what I want you to do. So this involves the will. So this is the normative reading of the Born rule, but notice what you learn from it. Not everything is subjective. It's the relation, the norm, that is objective, third personal, invariant. And that relation surely is telling us something about a deep aspect of reality. So this leads to a mathematical question that I want to end the talk by telling you a little bit about it. The expression that we've got, the phi matrix, depends upon the particular choice of the meek, the reference measurement in the middle. One would like to modulo that out of the story. The idea is, well, what we have is a deviation. The Born rule represents a deviation from the law of total probability. But we can ask, how big of a deviation is it actually? Well, that will depend upon the reference device. So the question that we'd like to ask is, what measurement device will minimize the distinction between these two entities? In a sense, that expresses conceptually Cubism's version of H bar. It says this represents the minimal engagement that an observer always has, that an agent always has when they act on a quantum system. So that's a mathematical question. And you can quantify it, for instance, by saying, oh, these are two matrices. Let me take the distance between the two matrices and find the phi matrix that minimizes the distance between this one and that one. And you can, for instance, introduce matrix norms. There is a very large class of matrix norms called the unitarily invariant norms. And you can say, well, let me minimize the norm distance between these two matrices over all reference measuring devices and see how small it can be. Well, it turns out that you can find a lower bound to it. And the secret ingredient for getting a lower bound to that distance introduces this mathematical concept, something that I'm going to call a seek. So we had minimal informationally complete measurements. Now let me talk about symmetric informationally complete measurements, or seeks. We can think of these as measurements or operators or quantum states. Here's the key ingredient. For any Hilbert space, for any quantum system of dimension d, we need to find d squared, not d, but d squared projection operators that satisfy a very beautiful and simple symmetry. namely that if we take the inner product, the Hilbert-Schmidt inner product, between any two of the ones up here, we always just get a constant number. Or if you want to think in terms of state vectors, what we get is that the inner product of any two of these state vectors is just this constant value up to a phase factor. If such a set of operators exist, then we can achieve the lower bound of the distance between so the distance between this and this is lower bounded by a certain quantity if for all reference measurements, if we can find a set of operators that satisfy this beautiful little symmetry, then we can achieve equality in the lower bound. And when we do that, we see really a stark expression of the difference between the classical equation, classical law of total probability here, and what the Born rule looks like when expressed in terms of the secret ingredient. It's just a very minor change. What happens is that this term P of R gets modified to D plus 1, the dimension plus 1 times P of R, and we subtract a little bit. But that difference makes all of the difference in understanding reality. It explains everything that we have seen in quantum mechanics, because everything that we see in quantum mechanics is a result of using the Born rule. Similarly, the Schrödinger equation, if you work through the Schrödinger equation, you can find a way of expressing the Schrödinger equation in exactly this kind of form. All it takes is that we have this secret ingredient to be able to use for the reference measurement. But here's a mathematical question. Do these seeks exist? Well, the question of their existence was first posed in 1999 when Caves, Schoch, and I were working on the quantum Diffinetti theorem, and independently by Gerhard Zauner in Austria, 1999. And we could see that it ended up that we didn't need the seeks in order to prove the quantum Diffinetti theorem, but the question was still there. Can you find a measurement of this variety? And that was long before actually that we knew that if such a measurement existed, the Born rule would take this very, very simple thing. In 2017, in the background here, I have a little bit of it. In 2017, a student and my postdoc, Blake Stacy, and I wrote a review article about the state of play of trying to prove whether these things exist. And here's what's currently known. What's currently known is that there is numerical evidence to very, very high precision, even to thousands of digits, that they do always exist in all dimensions up to 193, and then in some sparse dimensions where there are special symmetries that one can use. What we know now is, so that's numerical evidence, but actually analytical proofs have been given in all dimensions less than 53, dimension 57, dimension 61, etc. You see the full list here. We have come a long way in exact solutions since the 2017 review paper. Much of this is due to Marcus Grossel, who has really unlocked a lot of information about the structures. And maybe this slide is a little too busy, but there are other dimensions where you have an exact proof depending upon a certain conjecture in number theory. So after 26 years, no one still knows whether the secret ingredient for getting the essential quantumness exists after all. A formal proof hasn't been given in all dimensions. And a few years ago, about 5 years ago, it became clear why no formal proof had been found before. There was a shocking discovery that proving that seeks exist in all finite dimensions appears to be deeply connected to one of Hilbert's 23 problems that he offered at the turn of the last century. This is problem number 12. It has to do with algebraic number theory. And that problem, just to tell you just the bare bones of it, consider the unit circle in the complex plane. Here I've depicted the seventh roots of unity. Okay, these are the seventh roots of unity. If you look at their coordinates, then you find that the expressions for the roots of unity can be constructed by taking roots of roots of roots. So there's an expression in terms of roots. But there's also a transcendental function, the exponential function, that gives you a very simple way of expressing the roots of unity. So you can either express it in this complicated way, or you can express the roots of unity, the first root of unity, in this very simple way by making use of a transcendental function. What Hilbert's 12th problem is about is whether one can always do that for every algebraic number field. There we go. So we can ask, why would the representation of the Born rule, exhibiting its essential quantumness, care about Hilbert's 12th problem? So if one could find the analog of this exponential function for the certain algebraic number field that the seek problem suggests for its solution, then one would have much of the proof of seek existence. But why would the Born rule, why would the mathematical structure of the Born rule care about that? Well, I can tell you that most of the philosophers that I meet at philosophy of science meetings wouldn't care. They would still be hung on the idea, you don't believe wave functions are real. They have to be real. And they don't listen to anything else about cubism beyond that. But a physicist might smell that there's an opportunity to, quote Bohr, learn something of very great importance from this. So I hope I've given you an introduction to the philosophical aspects of cubism, but I hope I have also given you some introduction to the kind of live mathematics that cubism suggests to us and gives us something to do for those times when we feel like shutting up and calculating. You do that for a while, but if we ever solve this problem of the seek existence, I think we're going to learn, we will uncover a new kind of diamond that's buried within quantum theory. So that's all I've got for you. Thank you. Thank you for your attention.
Thank you, Professor Fuchs. This was a fascinating and a very foundational talk. I really appreciate. I can start with the question of my own. As someone trained as an experimental quantum physicist myself, I'm curious about the practical reach of cubism. Are there any directions, let's say something experimental or technological, where cubism leads to a different prediction compared to the other interpretations?
Oh, that's a very good question. Let's take the seek existence question. Cubism was the first to even suggest that one look for these things. Short answer is yes. We expect cubism to make quite an impact on physics. The seeks, for instance, it turns out that these seeks are optimal measurements for quantum tomography. So you as an experimentalist, if you want to build the best device you can for revealing what quantum state is being prepared under the assumption that there's a uniform distribution of quantum states, and you want to make the least number of measurements possible, then the device you should build is one of these seeks. If you want to generate optimally secure random numbers, then the seeks are the optimal solution for that. They're also optimal for entanglement detection. Most recently, we put a paper on the archive, a student and I, proving that with regard to a kind of quantum computation called Clifford group computation. This is a method of doing quantum computing where you only use Clifford gates because they're easy to build. But the way to get the computation universal is to inject into a circuit something called a magic state. It turns out that the seeks have maximal magic. This can be proven. So in a sense, you get the maximal speed up in a Clifford gate computation by injecting them with these kinds of states. So that's some of the experimental implications. People have done proof of existence experiments in dimension 2 and in dimension 3 for the seeks, and I'm working with a group in Japan. Hopefully, we will see a dimension 4 seek come out of an actual demonstration. So I hope that answers it a little bit. I wish I could have shown you this.
It does. Yes, thank you. So it's a question from Yogesh Tambe. He says, is wave function objective or subjective?
Well, you're going to have several talks. One of them is by David Wallace, and David Wallace is going to tell you that a quantum state is objective. And my version of that is basically David is saying, wah, they have to be objective because that's the only way to understand them. But the basis of cubism is that wave functions are subjective. If you want to know a quantum, so if you can see it already in the no cloning theorem. If I hand you a quantum system and I give it to you and I say, I have a quantum state for that system. Examine the quantum system in every way you wish. You can't find out what quantum state I have assigned to it. There's no physical measurement. That can be proven, and it's equivalent to the no cloning theorem. If you want to know the quantum state that I have for that system, you have to ask me. So in that sense, it's subjective. And a different observer, a different agent may have a different quantum state for that. And the quantum states reflect their probabilities for various measurement outcomes, their degrees of belief. So a quantum state now is a collection of degrees of belief in cubism.
Okay, thank you. So the next question is from Nikhil Kumar Shah Sahu. It's a quite long question. He says, decade-long experiments like the quantum eraser and delayed choice setups have discredited the older speculations about consciousness playing a decisive role in quantum phenomena. For instance, Yu's paper titled Quantum Mechanics Need No Consciousness presents strong evidence that the collapse of wave function is governed purely by physical interactions, without the need of any conscious observer. An irreversible physical measurement or record appears sufficient to resolve superposition into definite outcomes. Okay, the question is, in light of these findings, does consciousness still hold any actual relevance or theoretical space within the quantum physics today? Or has it been quietly evicted by the physics itself? Thank you for it. Yeah, that's a nice
just as with the last question, it's going to depend upon who you talk to. If you talk to Roger Penrose, he would say, no, consciousness is absolutely important for things. I would say cubism itself doesn't have any use for the word consciousness in it. It reimagines what quantum theory is. Quantum theory is a decision theory. It helps you make better decisions. What does it take to be an entity that makes decisions? Well, if you look at the decision theory book and the one that I liked showing, the one from Leonard Savage. If you read the introduction, it says, "Who can be a user of this book?" It doesn't ask, "Must the user of this book be conscious?" So in that sense, I don't think consciousness plays any role in understanding what quantum theory is. On the other hand, it is important for cubism that what the theory is referring to, what it's about, is how we make decisions based on what we do in the world. And whatever it is, I mean, maybe an AI can do that, or they can't yet, but maybe eventually they will. But that's what the subject matter is, as far as cubism is concerned.
Mhm. Yeah, thank you. I think as you mentioned the AI, the next question I think is in the similar line. What Dr. Bharat Pandey is saying, in today's rapidly evolving quantum world, where AI, quantum computing, and human perception increasingly intertwine, if we imagine the QBist observer as a conscious agent descending a staircase of quantum experience, each step revealing a new subjective update of belief, then how should we rethink the role of agency in shaping the very fabric of scientific knowledge?
Oh gosh. No, leave that question up. I've got to absorb it. I think that's
Yeah.
probably a very deep question, and one that I won't be able to answer so quickly. If we imagine the cubist observer as a conscious agent descending a staircase of quantum experiences, each step revealing a new subjective update of beliefs, then how should we rethink the role of agency in shaping the very fabric of scientific knowledge? Yeah, the slide of David Merman from his Nature article of 2014, when he had his epiphany and he had his epiphany in 2012 and wrote the 2014 article for Nature titled "Cubism Puts the Scientist Back into Science." Um, I surely feel deep in my bones that there's some insight to be learned from this, that we have discounted the role of agency in the world. We think of ourselves as insignificant little nothings. And what this view of quantum theory helps us understand is that we're not insignificant nothings. But now by we, it might be a broader concept than whatever I can put into a human brain. We might include big data centers if they can start acting autonomously. But I don't feel I can answer the question better at the moment. I would encourage the questioner to read a couple of my papers where I at least attempt to make a broader statement. One of them is titled "Notwithstanding Bohr," the notwithstanding Bohr, the reasons for cubism. Notwithstanding Bohr, the reasons for cubism is the title of the paper. And at the end of that, I think I address a little bit more of what's being asked.
Thank you. One last question for today. So it's from Vasudevaji. He's asking why combining quantum probabilities have to be different if they are really, after all, probabilities. Does it have any consequences to probability theory?
No, I don't think it has consequences for probability theory itself, because I think that probability theory is something that is defined a priori without reference to what particular world we live in. But what the probabilities in quantum theory refer to are not objective states of affairs, but what will come about by measurement actions. And what the distinct rule for combining probabilities is about comparing not taking an action to taking an action. And that's where you get a modification of how the probabilities should be combined. So it's true, the probabilities remain subjective, but what we learn is that if you ask the question, probability of what? it's the what that has changed profoundly. One used to think that probabilities were probabilities of objective states of affairs. And in quantum mechanics, we learn, no, my probabilities are about what arises from my actions. So that's what changes. Probability doesn't change. Probability of what? The what changes drastically.
Yeah. Yeah. Okay. Thank you. Thank you so much. I think this was wonderful listening to your talk. For me, it was like a new perspective of looking at quantum theory. Thank you so much for this wonderful talk, and we really appreciate your presence and taking your time out to deliver your lecture. Thank you so much.
Well, thank you all for having me.